Hello and welcome again to my Physics Online video lecture series. Today's video is meant to be more for working a few examples relating to Faraday's law. A few people have requested that I work some examples out, specifically tied to generators and or solenoids with Faraday's law, so that is what I'm going to do in this video. That also means that you should go watch the other videos and read through your notes on Faraday's law before attempting this video, because I'm not going to reinvent the wheel with Faraday's law. I will have a brief review of some things and then on to doing Faraday's law in this video. That is to say, I will briefly review the law, but the focus is going to be on examples, not explaining the law and how it works. So we can begin before working the examples by just recalling what it is that Faraday's law actually says from an algebra-based physics perspective. What Faraday's law is telling us is that the EMF induced, or the average EMF induced in a system, is given by the rate change of the magnetic field flux through that system, generally like a closed loop, for example. Okay. Now the request here is that I work through some examples that deal with either solenoids or the like a generator or something like that. So I will try to focus mostly on that kind of example today. So for our first example, we have a solenoid with 300 turns, each enclosing an area of 0.075 square meters with an external magnetic field applied to it in the direction parallel to the longitudinal axis of the solenoid. So before actually trying to solve the problem, let's kind of sketch briefly what it is that we have here. Solenoid consists of a bunch of windings like this. There are 300 of these windings. The longitudinal axis is basically this axis here that is sort of, you could think of it as the axis around which the coils are wound. You have a magnetic field that is being applied to this solenoid more or less in this direction here, parallel to the axis. So this is your B field, and then we're trying to figure out the induced EMF for this situation. Now to do that, we basically invoke Faraday's law. This right here is your induced EMF, whereas this is your magnetic field flux through the solenoid, and then N is the number of windings present. So basically what that means is that to solve this for the induced EMF, what we have is negative N times delta of the flux, which again is B dot A, divided by delta T. The negative sign we don't really care about in this case because we're just being told steadily increased, and we're trying to figure out the average induced EMF. It's just a magnitude. So this part is not so relevant because we don't have enough context to know the direction in which things are happening. So this ends up basically being 300 windings times delta of B dot S. So B again is 2 Tesla minus 0 Tesla. S, or A, is 0.075 square meters. Since these are parallel, since B is parallel to the longitudinal axis, B is parallel to A, and that means the cosine of the angle between them is 1. Remember that in a dot product you have to also take the cosine of the angle. So that one is just 1 in this case. Delta T is 0.025 seconds. And so you basically just plug all these numbers into a calculator if need be. Obviously this and this actually 0.075 over 0.025 is actually 3. So this ends up giving me a value of 1800 volts, as it turns out. So we have an induced EMF of 1800 volts for this situation. For our second example, I'm doing kind of what might be called a weird example, because I am specifying that the flux is going to change at a constant rate from its maximum value to a value of 0 in a time of 2 seconds, but the rate of change is constant. Okay, so we're assuming that the speed of rotation may be varied in order to make this occur, and so we want to know what the EMF is. So again, Faraday's law says that the induced EMF is equal to the number of loops, which in this case is 1, times the rate change of the field flux per unit time. So if I go back up to Faraday's law, I've rewritten this equation. This whole term, this term that I have circled collectively, is the rate change of the field flux. Now this rate change in the problem that I'm working has been declared constant. So we would have to figure out what the value is. A constant rate of change, for what it's worth, is akin to saying that I'm going to graph the field flux here, and I'm going to graph time here. And I've been told it goes from the maximum value down to 0 at a constant rate of change. So the slope of this line from maximum value to 0 is equal to that rate of change. That's just how slopes work on graphs of things versus time. So basically what I need to do in order to get this is, again, I'll plug in a 1 for the n, and I'll recall that I don't really care the direction of anything. We'll just have 1 for n times that slope. And that slope basically is from you could say this is from maximum, so B0 or B max, minus minimum. So this is B minimum, which is itself 0, divided by the delta time. And the delta time, for what it's worth, is, let's say this is 2 seconds and this is 0 seconds. So this would be 2 seconds minus 0 seconds. Now, the other thing to note here, as I said a moment ago, I got rid of the minus sign. In some sense, I didn't really need to, because this right here is already the negative of the slope, since I'm actually starting from this point and ending from this point as far as the numerator is concerned, the delta y, if you will. But I'm starting at this point and ending at this point as far as the denominator is concerned. So in some sense, that negative number out front is being absorbed into how I'm figuring out my slope. Okay, so this ends up looking like 0.8 Tesla, or 0.80 Tesla, times 0.60 square meters. And the second term was a 0 anyway, so I don't need to include it, divided by 2.0 seconds. Okay, so this comes out to 0.48 divided by 2 gives me 0.24 volts for this problem. All right, I'm going kind of quickly through these examples because I'm trying to get, let's say, 3 of them into this video, because I need to do one more example to really tie this together with the question that was asked. The assumption here, as I mentioned, was weird in as much as I assumed a variable rotation speed such that the flux rate is constant. So now I'm going to ask, what would happen if instead I had a constant rate of rotation? Would that lead to the same result? And the answer is no, because when you have a constant rate of rotation, basically what ends up happening is, let's say this right here is my loop, and this right here initially is the direction in which it's pointing. And let's say, for the sake of argument, that our B field also happens to be in this direction everywhere. So here I'd be able to say something like cosine of theta is 1, theta is 0. This area vector and this B field vector are parallel, so cosine theta is 1. Now let's say that I rotate my loop in such a way that now I have this as my direction for the area vector. And again, my B field remains pointing upward. Well, here now is the angle theta, and remember that this flux phi sub b is equal to b dot a, which is equal to b times a times cosine of angle theta. So if I come back here and label this other vector, this is the area vector for the loop. Remember that it's got to be perpendicular to the surface that it's finding an area for. So I labeled that as B instead of A. Here's A. You're looking at BA cosine theta, and so when you're trying to figure out what is the rate change of phi B, what you're really trying to figure out is what is the rate at which this whole quantity B times A times cosine theta is changing. Now, since B and A in this case are both constants, in other words, the total area enclosed by the loop and the magnetic field are both constant, I can actually pull them out of this expression, and I'm just looking at the rate change of my cosine angle theta as the thing that's driving the rate change of B. Now, going back to uniform circular motion, in which I have a constant rate of rotation, usually denoted by omega, I can state that the angle through which I have rotated, delta theta if you will, is omega times time, or I could say that the total angle in which I'm pointing is omega times time plus a theta naught. In this case, we're going to treat theta naught as 0. So coming back down to this problem, initially we're in this condition, so theta naught is 0, and then I've rotated through some angle theta. Well, this then becomes B times A times delta of basically cosine omega t. So rate change of cosine omega t. And as it turns out, that ends up being equal to the essentially like omega, or negative omega as the case may be, times B times A times the sine of omega t. It turns out that sine omega t gives you the rate change of cosine omega t. And that's, in some sense, reviewing back when you learned about oscillation. And when you learned about simple harmonic oscillations, we figured out that the motion of the mass at the end of a spring might be described by some amplitude times cosine omega t, but that was the position. And so if you wanted to find the velocity, that ended up being negative omega times A times sine of omega t. And so this right here can be used to solve this other problem, because v is the rate change of x, and x was given by cosine omega t. You could pull a constant amplitude out front if you'd like, and that ended up being a omega sine omega t. And so this means that omega sine omega t is the rate change of cosine omega t. that means that we can make use of all this to figure out what the rate change of the flux is through a loop, or for that matter through a solenoid, which just is a bunch of loops stacked on top of each other. So this brings us to our last example, which is for a generator. And this also kind of explains where this equation for the generator comes from. So suppose that you have a generator. It's got a short solenoid with 600 turns of coiled wire. We know the area. It's spun at a rate of 60 Hertz in a uniform magnetic field of known magnitude. We want to know what the maximum output EMF is. Now this is a slight departure from the earlier what's the average EMF, because as it turns out, if we come back up here, this equation is true, but this equation is true for any constant rate of spinning. And that means that this right here is giving us the actual value of the EMF, not just the average value, but the actual instantaneous value of the EMF. And so the instantaneous value of the EMF for a generator or any set of coils spun in this uniform magnetic field ends up looking like N times omega times B times area times the sine of omega t. Now notice that the negative sign from Faraday's law and the negative sign from this rate change kind of combine to eliminate the negative sign. So there's no negative sign in this equation for the generator. So we can write that equation again. That's N times B times A times omega times sine of omega t. Now, if we're wanting to look for a maximum value, we need to look at this equation and ask which of these things is varying in time, and therefore which of them has a maximum. Well, these three things are all constants. So these are all constant. So this right here is the only part of the equation that can be maximized or minimized. So this has a domain or a range, if you will, of -1 less than or equal to sine omega t less than or equal to +1. That's just how sines and cosines work. They have a maximum value of -1, they have a minimum value of +1. That's true for any real argument. Okay, so if we're looking for a maximum value, the maximum value happens when sine omega t equals 1. So my maximum induced EMF must be N times B times A times omega. That is N times B times A times 2 pi times F. This right here, 60 Hertz, is actually a frequency F, not a frequency, angular frequency omega. And so my maximum value here is 600 turns times 1.5 Tesla times 0.80 square meters times 2 pi times 60 Hertz. And you can plug all that stuff into a calculator to get your final numerical answer. The answer that you end up getting is 271,433.6 watts, and maybe a little change, so we could maybe call that 271 kilowatts of power. So that's how much power this particular generator produces at maximum. So that is 3 examples with a little bit of explanation relating to Faraday's law, to generators, and to solenoids. Hopefully you all find this helpful. And that's all for today's video, so thanks for watching.